Welcome to this video on the properties of the gradient. The gradient is one of the most important concepts in multivariable calculus with numerous applications in mathematics, physics, engineering, and computer science. In this video, we'll explore the key properties of the gradient and why they matter. First, let's recall the definition of the gradient. For a scalar function f of multiple variables, the gradient, denoted as nabla f, is a vector of partial derivatives. For a function of two variables, f of x and y, the gradient is the vector containing the partial derivative of f with respect to x and the partial derivative of f with respect to y. For a function of three variables, f of x, y, and z, we add the partial derivative with respect to z. Now, let's explore the key properties of the gradient. Property 1. The gradient points in the direction of the greatest rate of increase of the function. Imagine you're standing on a hill, and you want to climb to the top as quickly as possible. The gradient at your location points in the direction of the steepest uphill slope. If you follow the path of the gradient vectors, you'll take the most direct route to the top of the hill. Property 2. The magnitude of the gradient gives the rate of increase of the function in the direction of the gradient. Continuing our hill analogy, the magnitude or length of the gradient vector represents how steep the hill is at that point. A longer vector means a steeper slope. In mathematical terms, if we take the dot product of the gradient with a unit vector u, we get the directional derivative in the direction of u. The maximum value of this directional derivative is precisely the magnitude of the gradient. Property 3. The gradient at a point is orthogonal or perpendicular to the level curve or level surface passing through that point. A level curve is a set of points where the function has a constant value. In our hill analogy, level curves are like contour lines on a topographic map, showing points of equal elevation. The gradient at any point is perpendicular to the level curve passing through that point. This property is especially useful in physics, where the gradient of a potential field gives the force, which is perpendicular to equipotential surfaces. Property 4. At a local maximum or local minimum of a function, the gradient is the zero vector, assuming the function is differentiable at that point. These points are called critical points. Think of standing at the very top of a hill, a maximum, or at the bottom of a valley, a minimum. In both cases, there's no direction to move that would increase or decrease your elevation the fastest. All directions look flat locally. This property is fundamental in optimization problems, where we're trying to find the maximum or minimum value of a function. Property 5. The gradient operator is linear. This means that for scalar functions f and g and constants a and b, the gradient of a times f plus b times g equals a times the gradient of f plus b times the gradient of g. This property follows directly from the linearity of derivatives and makes calculations with gradients much easier. Property 6. The gradient follows a product rule similar to the one for ordinary derivatives. For scalar functions f and g, the gradient of f times g equals f times the gradient of g plus g times the gradient of f. This is analogous to the product rule for single variable calculus, where the derivative of a product is the first function times the derivative of the second, plus the second function times the derivative of the first. Property 7. The gradient satisfies a chain rule. If f is a scalar function and r of t is a vector function, a parameterized curve, then the derivative with respect to t of f composed with r of t equals the dot product of the gradient of f evaluated at r of t with the derivative of r with respect to t. This property is essential for understanding how the gradient transforms under changes of variables and for working with functions along curves in space. Property 8. The gradient can be seen as a linear transformation. It maps a vector v to the directional derivative of f in the direction of v. Specifically, the directional derivative of f in the direction of v equals the dot product of the gradient of f with the unit vector in the direction of v. This viewpoint connects the gradient to linear algebra and helps explain its geometric properties. The gradient has numerous applications in the real world. In physics, gradients appear in electromagnetic theory, fluid dynamics, and thermodynamics. In computer science, gradient-based optimization algorithms are fundamental to machine learning and deep learning. In engineering, gradients help analyze heat flow, stress distributions, and electric fields. In conclusion, The gradient is a powerful tool in multivariable calculus with properties that make it essential for understanding how functions behave in multiple dimensions. Its geometric interpretation as the direction of steepest ascent and its relationship to level surfaces provide intuitive ways to visualize and work with multivariable functions. Whether you're studying pure mathematics, physics, engineering, or computer science, a solid understanding of the gradient and its properties will serve you well. Thank you for watching.